Hi, my name is Lauren Shore, and today I want to spend a little bit of time talking with you about programming with MATLAB. And the objectives for today's talk include introducing you to programming with MATLAB, including how you program in the MATLAB language and some details about the language, and also some of the development tools that support the programming environment in MATLAB. I also want to show you how to program effectively in MATLAB, and that will mean several different things, using the right tools and using the right functions and how to find what you need. And finally, I want to demonstrate a range of programming styles that MATLAB supports. I'll be using a lot of interactive tools, the command line and others, as well as scripts and functions. And unfortunately, today I don't have time to go into object-oriented programming, but that is something that is fully supported in the MATLAB language. The demo I want to talk about today is how to write an automated script to analyze the possible wind turbine output, power generation output at various locations, so that we can create some sort of automated system for analyzing where we might like to place a wind turbine. And the way I'm going to do that is I'm going to interactively look at some data that's been collected. It consists of measurements from 3 sensors for velocity at 80 meters high from a relocatable wind tower, and a temperature measurement at 3 meters high. And we're going to collect that data for a full year, hourly, or maybe multiple years. And we want our automated process to be able to import the data and do pre-processing. Now I'm going to have to do some pre-processing, and we want to make sure that that can be done automatically as well. Once I get the data pre-processed, I want to take those wind speeds and figure out what the wind speed probability distribution function is, because I'm going to need that in order to estimate the average power output for each turbine location. And then I want to be able to automate that to run on data from all the other locations in order to ascertain which one is the one that is the most productive. The next thing I want to talk about is how I'm going to go about calculating the average turbine power. And what you see here is an integral. I have to integrate over the velocities the probability distribution function of the wind speed times the wind as a function of velocity for the turbine power curves, and those are generally supplied by the vendor of the tower. And so you usually know at the time you're doing these experiments which vendor you're going with, so you know what that wind turbine power curve is. So I need both of those pieces of information in order to calculate the average power, and then therefore what the capacity factor would be. And I'm going to go to MATLAB now and show you where I start. So let me come to MATLAB now, and here we are. To start, I want to show you the code that we end up with in the end for automation. And what this is in the editor here you can see there's some what looks like to be English words. These are comments in the MATLAB language preceded by percent signs, and percent just makes the code be divided up into different sections. So I have my first section here and the next section, and what I would like to do is, you can see I get a list of the files in the directory, and then I run file by file through and do the analysis for each one. And so what I'd like to do now is just show you how that works. So I'm going to just run that script. And here you see a whole bunch of figures that came up with wind distributions from a bunch of different tower locations. And I'm now going to close those. And I can show you what happened back in the command window. In the command window, you'll see that when we started, Wind Analysis Automate first showed me what files I was going to process, and then it went through and processed the first one and told me what the capacity factor was, and the second one and told me the capacity factor, and it kept track of all of the different capacity factors. So at the end it says that the capacity factor was the highest at Tower 4, and so we would have our answer by the end. So my whole goal now for the rest of this talk is to show you how we might get to such a place. To do so, what I need to do is close out what I'm showing you here and sort of start from scratch, some fresh MATLAB. So what I'm going to do is use this shortcut to clear everything out. And if I take a look, I'm right-clicking here and editing this shortcut. It's on my Quick Access toolbar. I happen to have something that's called calling a bunch of MATLAB functions, and I clear variables, clear classes, clear the command window, and close all the windows. And so since this, like the other things on my Quick Access toolbar, are things that I use often, I park them up there so that I have ready access to them. So now what I'd like to do is I'd like to show you a sample data file so that we can begin looking at the data and figuring out how we need to analyze that. And for this, I'm going to come to the current folder directory, locate windata.dat, and I'm going to open it outside MATLAB. And this is typical of data files that you might have seen before. It's got some headers at the top, time, at the 80 meter, the speed, yearly average speeds. So you see we go from July 2007 all the way to July 2008, and they're hourly averages. So hourly data points. So we have the three velocity sensors, the three speed sensors, wind speed, and the temperature at 3 meters. And so we need to get this into MATLAB somehow. And so if I come over here onto the home tool strip, you'll see that there's something called import data. Now, I said we wanted to automate things, so why am I showing you this interactive tool? Well, I'm going to explain as we do this. You see this tool opens and it tries to make its best guess based on what it sees in the file, how to import the data. This time particular one, though, could actually be introduced as either a string, but I'm going to actually choose a date format here, and I'm going to choose the one that's days, months, years, hours, and minutes here, and select that. And you see when I hover over any one of these, you'll see a number underneath that instead is represented by 10 June 2007, 1900, for example. But underneath it's numeric, so I'll be able to do numerical calculations on it now that I know it's a date. And I could change these different labels. I'm going to bring them in by columns as default. It's discerned what format I need. And so what I can do is I can come over here and I can say just import the data, please. And it's scanning the file, and you see that it says that there were several files imported. And if we come over here, we can see in the workspace browser that we've imported 5 different arrays: the temperature, the time, and the 3 speed vectors. Now, one other thing that I can do, and this is going to serve us in the automation section, is not only can I import the data itself, but I can generate a function for importing this data, so that if I have data that is similar in form to this, I can reuse this function to import that data again. So let me save this file. We generated some code, import file here, and you'll see it's got comments in it. It's a function. It's got some inputs and outputs. It has some help, and calls a bunch of MATLAB functions to get some of the job done, and then it returns 5 outputs. In fact, if I type help import file, you'll see that there's an example that comes out, and what I can do is I can clear my workspace now again, and I can come here, and type help import file, and I can take this example here, copy and paste it. And if we look in the workspace browser, once again, we see those same 8,776 values for each of the vectors that we've got. Now, the next thing that I typically do is I like to take a look at the data. So what I'm going to do here is I'm going to select time and the temperature, and I'm going to come to the plots tab on the toolbar, and you'll see that the plots that could take 2 inputs, the various plots from various add-on toolboxes as well as MATLAB itself, show up. And I'm going to just do a regular plot. And here we see a plot that I can do. And this shows the data very well. And let me bring that forward here. I want to bring my figure forward. And I'm going to put it into the desktop so that we don't lose it for a moment. Now remember, I loaded that data in the date format into numeric form. But when we see this figure, those numbers don't really mean anything. So I might want to try to find a way to do something about that. So if I come over to this function browser here, I can say, let me look for something that will label dates. And you see I get date tick. And so if I come along to date tick, I can start trying to apply it to the current figure that we've got here. And if I type slowly enough, it starts to try to help me to say, so I can figure out what the input syntax is. So I'm going to take the x-axis, and the format I'm going to do is month, month, month dash year, year. I next want to label the axes so that we remember what they are. So I'm going to put a label on the x-axis, which is the time and date, and the y-axis is temperature. And you can see as I'm typing that MATLAB changes color and shows me that the string is completed when it turns purple. And now what I'd like to do is start analyzing the data. And one of the things that we can see in this figure here is that when there are temperatures that are in January, because it's the northern hemisphere, that are quite cold. So we see that it's warm in the summer, cold in the winter, and some of those cold temperatures end up being below 0 centigrade, which means that things could be frozen. And so we need to worry about whether the velocity sensors are frozen. So we'd like to find times when they might be frozen and figure out how to take that data and get it out of our data set so it doesn't skew things. So in order to do that, what I'd like to do is I'd like to take my my data, my three velocities, and average them because they're fairly redundant, but it'll help me reduce some of the noise in them. So I'm going to take the three vectors and basically concatenate them into a matrix, and I'm going to call the mean function on them. So I'm going to calculate the mean, but first I'm going to put vector 1 in, v 80, and I can use tab to help me find the names, average 1, V80, average 2, and V80, average 3, and and I'm going to end that concatenation. Now I've got 3 columns, and I want to basically average and get 1 column, so I'm going to average on the second dimension, and that's how I'm going to use the mean function. So this was really nice. I didn't have to use a for loop. I was able to act on the whole array all in one step. And now what I'd like to do is think about times where the temperature is low and perhaps the wind speed is low. So let's take a look at that. And the way I would do that in MATLAB is very nice. I don't have to go through element by element with a for loop. I can just use what's called logical indexing. And so the first thing I can do is I can say, find me the index where temperature is less than 1. And the reason we have it be, or less than 2, let's say. The reason we have it less than 2 is if it was below 0 before and then came above 0, even if it's up to 2, some of our sensors could still be frozen a little bit. So we want to be a little conservative there. And then I also want to find the conditions where the velocities from the average velocity are really small, because that might mean that they're iced over. So I want to see where the the average speed is less than 1 meter per second squared. 1 meter per second, excuse me. And I can combine these two because these are just zeros and ones. Some logical operators will allow me to work on this, and I can say the total index, the total locations of indices where I want to think that icing may have occurred is going to be the icing condition for temperature, and element by element, make sure we take that condition in account as well as the condition of the speed being too low. And so if we actually were to take a look at IDX total, I can click here and I can open the selection in the browser here. And if I go to around 4,000, sorry. Let me go a little more slowly here. You see most of these zeros, so these are all good points. They're not points where things are iced. But as I move on up here, now I'm getting near 4,000. I happen to know that there's a point near here, point number 4018, that has both conditions true. So that's interesting to know. So there are points like that, and I would probably want to remove them from my data set. And the way I can do that is with the following syntax. I can take the times that are associated with the IDX total and just say take those times and delete them from the time vector. And I can do the same thing. I used command line recall there, the up arrow, to do this for V average, the average speed, and for the temperature. Well, now we have the velocities culled so that we have the right data that we have. We've gotten rid of the bad data points, and we'd like to see what the wind distribution looks like. And for that, I would like to calculate and display a histogram. And the way I can do that is I can figure out how to bin the data first of all, and I'm going to make a vector that goes from 0 in steps of 0.5 up to the maximum of V average. And I'm going to maximize my command window for the moment so you can see what that is. And basically I have something that is 43 elements long, and you see the points are 0.5, 1, so on. If I wanted to go in just a single step, I could have left out the colon and 0.5, and it would have just stepped in steps of 1 there. So that's how I can create a vector very quickly in MATLAB. And now what I'd like to do in a new figure is create a histogram. And so I'm going to create the histogram with the data V average and my bins. And here you see the data that we have. This is a raw histogram, but we'd like to fit it to an analytical distribution so that we can characterize it. Now, typically in wind analysis and a lot of the physical fields, things are processes are governed by what's called a Weibull distribution, which has two different parameters that control it. And so what do I do? How do I find this? What if I don't know exactly what to do? And so what I can do is I can look in the documentation here from the desktop, and I can say I want to fit a distribution. And you can see I have something here called fit dist, and that's something that I'd like to use. So let me first look at the help for it, and here's the full page of help. And you can see that I can give it the data and the distribution name. And the distributions that we can choose from include a whole list of them here in the documentation, and one of them includes the Weibull distribution. Okay, so let me come here and say we're going to create our probability distribution for the wind is equal to fit dist of the speeds that we've got, and I want to tell it that it's a Weibull distribution. And what you see here is that it tells me it's a Weibull distribution, and it has some parameters for A and B for the Weibull distribution function. And so I can use this later on in order to characterize the distribution so that I'll be able to do the integration. Now I've been doing all of this by hand first, and what I'd like to do is now move to a situation where I could automate this just a little bit more. So I can actually come to my command history here, and I could pick a few commands. Pick a few commands here. For example, I have some that I've selected here. Load in the data. You can see that it's the import data here. Make my plot. And calculate the average velocity, find the icing conditions, delete the data that we don't want, calculate the bins, and the histogram. And I can right click and I can say create a script. And what happened here is it put this information into an editor, the editor, and I can save this. So let me save that now, and I can say it's my script here, and I can clear everything out that we've got done so far, and now I can come and I can just run it. And you can see from my script we come along and we run some of that again. Now I'm going to move from this to a script that I already have working to show you a little bit more about scripting, and so that I can move a little more quickly rather than you watching me type the whole time here. Okay, so I'm going to clear everything again, and what you see here is this collection of MATLAB statements that I'm going to tell you more about. So I'm going to make the editor maximized for the moment so that you can see what's going on. And you can see what we have is these are comments in the file, and they're divided into sections using %% rather than just a single comment character %. And what I can do is this lets me organize my information in my file. You can see I can take sections and make them smaller so that I can just get a high-level view of what the file has in it. And because I've got this file, I am documenting what I'm doing. So I actually have got here prose in these comments that shows and describes what each step is. So let me come along and do a run in advance. And I use run in advance so often that it's one of the items that I've put on my quick access toolbar. So let me make this regular size again, and let's come along here and evaluate the first set of comments, load in our data, make our plot, and there's our plots of our data. Let me come back here. I'm going to calculate the mean like we did, determine the icing conditions, and there we have plotted on top of it those points that were bad points. And I'm going to make the histogram here and do some extra labeling that I hadn't done. And the last thing that I just show here is wind speed distribution that has the wind speed histogram and the fitted Weibull distribution on top. And the way I got that was with the histFit function, which was another one of the functions that came when we were looking up here in the help. And so now I'm ready to come back and talk about that power curve for the turbine. And so let me come back to the slides here, and let's talk about that for just a moment. Okay, so here in more detail is information about the wind turbine power curve. And you'll see that there are 4 regions that the power curve is divided into. The really low velocities or speeds, where there's basically not enough wind to power the turbine. Ones that are really high, which make it dangerous to operate because things might fail, and so it gets shut down on purpose once speeds get over a certain point. And then the 2 other regions of interest, Region 2 and Region 3. Region 3 is the sweet spot. It's between the rated power and the power when you cut out. And that's when the wind turbine is working at maximum efficiency. And then in the region between the cut-in speed and the rated speed, you see that things go basically according to the formula that's written there. Whatever the rated power is times that v squared minus v in squared divided by v rated squared minus v in squared. So we would like to be able to talk about that and use that back in MATLAB. So let me come back to MATLAB now, and here we are. And I'm going to look at the code in more detail here, and you can see here I've got the turbine power coefficients from a particular manufacturer. So a megawatt of power, the cut-in speed is 2 meters per second, the rated output speed is 14 meters per second, and the cutout speed is 25 meters per second. And then here you see that for the power V bins, what I've done is I've taken our V bins and basically said I'm going to calculate the power bins, and it's just that formula that had the difference between the squares of things divided by the other ones. Okay, so that's the power curve, except for in locations where V bins is less than V in, and I'm using that logical indexing again. Wherever those were true, which is the low end, I'm going to put 0. And when the V bins is greater than V out, in other words, the cutout speed, we're going to make them 0. And when we get to the sweet spot where it's between the rated speed and the cutout speed, we're going to make it that constant value. And so now I can come along here and I can plot that. And let me go and plot this. And that's the curve that you saw in the other picture on the slide. And so there's our power rating. And now to calculate the average turbine power and capacity factor, what I need to do is do the integration. And so we have to integrate the power at a given velocity and the velocity probability distribution function there and integrate them over the range of possible velocities. So the first thing I need to do is calculate the probabilities for the velocities, and so I do that taking our wind distribution and using the probability density function calculation to calculate the density as a function of bins, and I take that times the power bins that we had, integrate them together, and use trap Z, which will do the numerical integration for us and compute the total power, the total average power there. And then I'm going to calculate the average, the capacity factor as well, which is the average power that we calculate divided by the rated power. And you can see this particular turbine location has a capacity factor of about 27%, and that actually is pretty decent. You usually don't get capacity factors much beyond somewhere in the 30s if you're really, really lucky. Okay. So now we have a script that does the analysis for the wind tower at location that we have stated at the top, which was winddata.dat, the data from there. We have the analysis done. What we'd like to do is now figure out a way to automate this and make it into a function so that we can work on any different data set for wind turbines. But before we do that, we want to make sure that this is the most efficient program that we could possibly have created. And so the way we're going to do that before we run it on multiple files is run and time instead of just run. And you can see that up here in the editor tool strip. So I'm going to go ahead and run and time this, and you can see the whole program run. And I'm going to come over to the profiler window that comes open. And you can see that we spend a bunch of time in the wind analysis script itself. And some other things that it calls. And I'm going to delve into what happens in wind analysis, even though it's fairly short running so far. So now I'm delving into wind analysis, and one of the first things you see is lines where the most time was spent seem to be mostly related to date tick and various graphics, hist fit, date tick, hist. And there's one line 13 that has the import command on it, and of course we need to import the data, so we will need to be able to do that regardless of how much time it takes. We want it to be efficient, of course. But now I want to take a look at a little more of the report to see what goes on. One thing we could do is we could delve into date tick and see why it's taking time. I'm not going to do that right now because we already know we have graphics in our report from playing around that we might not need for the final report. Now in the profiler report for the file, you see that there's lines of code that are highlighted in various shades of red. The darkest shades of red are lines that take the most amount of time, and you can see that it's import and it happens to be graphics related. The lighter red ones are still taking more time than some of the rest, but are taking less time than the longest ones. And we have a bunch of figures and plots in here that we don't need. We have one I think that we'd like to keep, the histogram with the fit on top of it. And so I'd like to show you what I can do now in order to change the code so that we get the most benefit out of the work that we did without putting in unnecessary work as well. The way I'm going to do that is I'm going to come over to the current directory, and instead of watching me type, I'm going to compare our script wind analysis to wind analysis function that I've created already. And we're going to take a look at these by comparing the selected files. And what you see here is at the top there's you can see differences on each side, what's in one file versus another. You see a lot of things in the script on the left that aren't in the function on the right. What you see at the top is the script doesn't have a header, but the function has a header saying that there's a single input, the file name, and an output, the win data that we need. And the comments are the same. And then since I'm not hardwiring in windata.dat, I let the input name, file name, be something where I extract the actual file name out of the parts of the file name. So if someone gave me a full path to a file name, I could get the name of the file itself alone. And we did the import, of course, and have the same data variables, not with the same data, but the same variables representing the data. Now you'll see next that I'm removing the code that has the next visualization in it. That's something that we don't really need. That was for when we were exploring. And you see many lines of code are the same. It says there's 11 unmodified lines in the next part. Then you see we doing the selecting the points that are suspect, the icing, and we're going to remove them without looking at the plot in between. And we continue on, and instead of plotting the histogram and looking at that, we simply take the data and the bins and create the distribution function that we need, the probability distribution function for the wind velocities, and we put them in the bins that we need using that same formula that we were using before. And we do all the same calculations until the end. And now you'll see that what I'm doing is I'm putting the data that we would like to return, and there happen to be 7 pieces of it, the time, the temperature, the average velocity, and so on. And instead of returning them each as separate entities, I'm putting them into what's called a struct in MATLAB, a MATLAB structure, similar to structures in other languages. And that way I can pack all my outputs into a single output, the struct, win data. And that's really a nice way to return things. So in the future, if I want to return some other information that I've decided is important, people who use this or other routines that I have that use this will automatically get that extra information without having to change their code. If they wish to access it and use it, of course, they might update their code, but they get the information there without their code breaking because it's still a single output regardless of what's in there. I'm now going to try applying my function to the text file that we used before, the original data file, windata.txt. We hopefully will get the same answer that we had before. And what you see here is the result of our function. We get the one plot out, and we get the printout at the end that says information about the wind data profile there, including the capacity factor, which is about 27%. And I happen to have another file lying around, tower location 1, and I can apply my function to that new location as well. And if we do that and rerun it, one of the things you'll see in this plot is the plot is labeled with wind speed distribution from tower location 1. So our plot is telling us about itself. It's self-documenting a little bit. This particular location has a capacity factor of about 20%, and so if we're choosing between wind data location and tower location 1, wind data location has the superior capacity factor, so we would choose that. So now we can see we can apply this to multiple files and or different files one at a time. And I'm ready to start thinking about how I might, now that I've got this function, apply this analysis to a bunch of different functions, or a bunch of different data rather. And so I want to look at the automation function that I've got here. And I'm going to open that. And what you see here is another script, it turns out, in MATLAB. And we start off with the title there, and we're going to get the names of the files that happen to be in the current folder under hidden in another folder inside the current folder, and you can see there happen to be 6 location files there. And so I'm looking for the file names in that particular directory, and I'm going to process those. I'm going to print the names out and process them. And then we're going to loop through each one, and we're going to allocate a struct for each one of them. So each of the 6 is going to get one element in the struct to output all the different values. So we take the file name, we say we're analyzing it, we call the analysis function, and see what the picture looks like. The full file is really nice because it lets us take files that are available to MATLAB because someone gave the full path to them, and full file lets you be agnostic about whether you're starting on Windows or on another platform, for example. So now I can take this full script and I can hit publish. And what it's doing is it's running through that for loop after it finds the file names, and it, in this case, creates an HTML file. You can also create other file types out of it. And you see it's self-documenting. It says we get a list of the files, and you can see those files as we scroll down just a little bit. And we could hand this analysis off to someone else. So there's the file names, then we're going to loop through them. Each one we loop through has information. It says which tower location and the capacity factor and the probability distribution function, as well as the Weibull distribution that goes with it. And so we go along there, and as well, while we're doing this, we're also collecting all the information from each one of these, and towards the end, what we're going to do is figure out which one had the maximum capacity factor, that's what you see in the code here, and print it out at the end. And then we use the opportunity at the end to also save the data should anyone want to see the full analysis after we're all done. So that's the way we do the analysis. We have automated things in both a script and a function. We're using both. So we have our function that operates one file at a time, and it doesn't care what file. You have to pass that data information in. But what our script does is calls that in an intelligent manner and collects the output in a way for others to see the analysis that we did. I'm now ready to come back to the slides for a moment and remember how we got to where we got just now. We started working interactively. We took advantage of the import tool to understand the data that we had, and then we automated that by creating code from there. We also worked at the command line for a while to make sure we were doing something that was sensible. We then used the command history to extract some of the functions that we used, and we created an automated script with comments and sections, which we then also used the profiler on so that we could assess the performance and get it performing the way we wanted. In this case, we removed several of the plot functions so that we had a generalized function in the end that was able to handle any kind of number of files, and then we wrote a script that called that function at the end. So while we were doing this, we were using MATLAB as well as the statistics toolbox functions for doing the work with the probability distribution functions. Now, I've been talking about a range of programming techniques, if you think about it this way. I started at the command line using values and variables, and then I started using a script where I had the variables as well as graphics. And eventually we ended up using a function, and in that function, even towards the end, we returned structure containing information that was related, but not all, so that you could put it in one matrix because they were different kinds of pieces of information. So we were using a range of different programming techniques to achieve this goal, and that's not uncommon to use the whole possible range of programming techniques when you're working on a problem, from prototyping all the way to the end of creating a program that will last. There's a way of extending what we've done here now, and we can make our program even more robust and more maintainable, and I'd like to talk about that for a few minutes now. So now what I'd like to do is compare the function that we created, wind analysis FCN, with wind analysis FCN2. And what you'll see first is that the major difference is all in the code at the beginning. The inputs and outputs are the same as before, and the bottom of the function is the same. So all I've done is added some information. And what I'm doing is putting in some information to handle some other cases. So the first case I handle is the no input case. So if nargin equals 0, that's nargin, number of input arguments. And so if someone doesn't supply an input, what I can do instead of tossing an error is I can give them a dialog so that they can choose the file that they would like to process. And so that's something that you might do to help make your processing easier for the users who are going to do it. And the next thing I do is I check to see if the input is a string using validate attributes. And I look to see if it's a string, a character array, and it's a row. Because if it's not a character array and a row, there's no way it's a valid file name. After I've ascertained that it's a row and a character, I look to see if that file name is indeed a file and if it exists. And if it doesn't exist, we put out an error message so that our users know what happened. So let me show you this in action just very briefly. I'm going to get a result from calling wind analysis function 2. And I'm going to call it first with no inputs. And what you see happen is we get this dialog that lets us choose a file. And we can choose one, for example, our tower location 4, which by the way happened to be near Logan Airport. And we run the analysis there, and that's nice to see. And now I can call this function again with a number, and you can see that I get an error message, and it says that it expected a character input, and instead I gave it a double, so that it was not able to process that input as a file name. So we've made this so that it's much more tolerant to different kinds of input. We've made it so that you get a sensible answer out or a sensible diagnostic out if you've given it something it can't handle. So in terms of refining and improving the code, you can make things more maintainable. I've showed you using a certain data type, a structure already. There's other things you can use like cell arrays and objects is not a topic I'm really covering today. And you can also use different function types, and I haven't had a chance to talk about those today, but they really make your code much more easy to maintain and read for the future, whether you're passing it along to someone else or you are the person who has to read it again 3 months from now. In addition, I can make the code more reusable by letting the syntax be more flexible. Instead of just using nargin for testing for no inputs and one inputs, I might have it so that I might be able to give maybe a list of files, and I might be able to do that using something called varargin or variable input arguments, and I can do something similar with variable output arguments. So I can make this code more general purpose depending on what I want to use there. I can also make it more robust. I used validate attributes to check that things were that input file name was a character row array. I can use validate string error input parser, various other routines to help check the inputs and make sure that they are suitable. Also in R2013A, there's new functionality called unit testing, and it's in a package called MATLAB.UnitTest, and it's something that's very useful. It's very similar to something that's out there called XUnitTest that's used in other languages, and now there's a good way of doing unit testing in MATLAB. In addition, I showed you using a lot of our development tools, the editor, the debugger, and the profiler. I did not get a chance to show you the code analyzer. There are additional MATLAB programming features besides the ones that I've been talking about, and those include, for example, object-oriented programming. And for the benefit of you who don't know much about object-oriented programming, if you remember that range of programming techniques, I had different kinds of data going from values and variables up to structures and more complicated collections of information, and I had, starting at the command line, went to a script and then a function. If I take related data and functions and sort of put them together, I can put them together in what's called a class, and then the functions in the class, which are called methods, are able to operate on instances of the class, the objects, and they're created in such a way to be tuned to the kind of data that's stored inside that class. And it's a very useful programming technique. Having said that, all the different programming techniques are useful, and you don't use just one or the other. You use all of them at various times. We also have parallel programming capabilities with the Parallel Computing Toolbox, and it allows you to speed up MATLAB applications on multiple cores, GPUs, clusters, the cloud, and you can handle large data sets by distributing them across MATLAB workers. And as we've done in other cases, we try to have some simple constructs that you can use to access this in case you're not interested in the details of parallel programming. And they include support in various toolboxes and a parallel for loop and creating arrays on your GPU to advanced constructs like writing your own MPI code or CUDA code or creating your own jobs and tasks to make the parallelism something that you provide yourself at a lower level. So today I've talked about sharing results from MATLAB in one way. We had the automatically generated reports where I used the publish command. There's other ways to share information from MATLAB as well. You can create graphical user interfaces. You can package a collection of your files up as a MATLAB app. You can deploy applications to other environments. For example, .NET assemblies and Java environments. And you can automatically generate standalone C code from a subset of the MATLAB language suitable for running in other situations. So there's a lot of ways of taking your hard work and making sure you can share it with other people or in other environments that are a good target for your work. In addition to sharing results, I want to give a high-level summary of what we did today. I talked about MATLAB as a high-level language. It's matrix-based. You got a little glimpse into some of that when I created arrays and concatenated them and worked on them all at once. MATLAB has full support for math and graphics functions, as well as all the traditional programming language features that you've seen and more, flow of control, for example. I also showed you some of the interactive development environment, the tools, the debugger, the editor, etc., and visualizations and help that you could use in order to make sure that you're as productive as you could be writing your MATLAB code. And I talked about the range of supported programming styles. You saw me use the interactive command line, scripts, and functions. And as I said before, I didn't have a chance to use object-oriented programming, but it is a full-fledged member of the MATLAB programming language capabilities. And it might be something that you'd like to use in appropriate situations. Thanks for your interest in learning about programming in MATLAB.